Okay. All right. Okay, discontinuities is what we're going to talk about today. And we're actually going to spend pretty much the whole week talking about a function being continuous or discontinuous. So today we're going to specifically look at types of discontinuities. So this is something that I normally would cover in pre-calculus, but I did not cover with you guys, so it's going to be the first time you guys have seen it. There are two types of discontinuities that we can have, but underneath non-removable discontinuities, there's a couple different ways that can look. So a removable discontinuity is just a hole in the graph. So it can look like this. It could look like this. It could look lots of different ways, but it's just an open circle somewhere on the graph, right? And it is called a removable discontinuity because you could remove that hole in the graph by adding just one single point to the function. All right, so it can be fixed with one point. Non-removable discontinuities come in the form of jumps and vertical asymptotes. So if you have a jump where it may look something like this in the graph, or if you have a vertical asymptote, so this, may look something like this, where you got that vertical asymptote. Sometimes the vertical asymptote might, like in natural logs or something, might look like this. Might just be from one side. It might go to positive and negative infinity, but you have quite like this. Non-removable discontinuities cannot be fixed with a single point. You would have to take a piece of the graph and slide it up or down, or asymptotes really can't. There's nothing you can do with them. The whole point of an asymptote is that it gets closer and closer to a point, but it never touches, right? So these cannot be fixed. All right, questions? All right, so there are several things that can cause a discontinuity. A negative underneath the square root is going to give you a discontinuity. A 0 in the denominator of a fraction. A number less than or equal to 0 inside of a log. A piecewise function that has a hole or a jump. And some trig functions such as tangent and cotangent, secant, cosecant. Not cosecant. Yeah, cosecant. Are going to have asymptotes just built into the way that they look. So what most of your homework is going to be asking you to do tonight is to find any discontinuities. And a lot of them are going to look like this. They're going to be rational functions like we see here. So if I look at this first one, what I can do, and let's use the Scott Wood theorem here and type this into Desmos. He'll be so happy to know that y'all named a theorem after him. Alright, so if I look at this, it looks like a rational function. And I can tell right here at 2, I've got a vertical asymptote, right? But that is not my only discontinuity. Alright, so just looking at the graph that we see, it's difficult to tell where the other discontinuity is going to be. But it is anything that will give me a 0 in the denominator. Okay? So, to figure out what will give me a 0 in the denominator, I could factor that denominator. So, if I do that, I warned you guys that you would need to factor for like the rest of your lives, or at least as long as you're in math classes. So I would factor the 2 out. X squared plus x minus 6. You don't necessarily have to do that, but I'd like to. And we'd have, what here, plus 3 and minus 2. And so, if I haven't factored, it's easier to see what values would give me a 0 in the denominator. So, which values give me a 0 in the denominator? X equals 2 and x equals negative 3. So, if those values give us a 0 in the denominator, they are discontinuities. So we know we have discontinuities at both of these places. The question is, are they removable or non-removable? Well, I can see right here at 2, I have a vertical asymptote. That's a non-removable discontinuity. But at negative 3, let me zoom out a little bit so negative 3 is showing up right here. It looks like a solid line. But if I can get it to go exactly to negative 3, which I don't know if I can. Right here. Well, did you guys just see it turn to undefined? Oh, it was there. There it is. Negative 3 is undefined. Right? So, there's a hole in the graph at that point. So, looking at the equation, because we'll be doing this without Desmos. Looking at the equation, how can we tell that? Okay, these cancel. If the term cancels, that tells you a hole in the graph, which is non-removable. I'm sorry, removable. Removable. Holes are removable. And if you have something in the denominator that does not cancel out but gives you a 0, that is going to be a vertical asymptote, or we could say that's a non-removable.
They made us do this with like exponents of like x to the 3rd, like on the bottom.
Yeah, you can do that.
Yeah, they made us do that.
Yeah, they can make you do that, but we'll stick to things that are.
We'll just stick with this.
All right, so if we want to look at the second one, we could just factor. The top factors into x plus 2 and x plus 3. The bottom factors into x plus 3, x plus 1. Have I factored that correctly? Okay, so discontinuities. X equals negative 3 and x equals negative 1. Negative 3, is it a hole or vertical asymptote? It is a hole because the x plus 3's cancel. Negative 1, that one, vertical asymptote. Because it is okay to have a 0 in the numerator. Because 0 divided by 5 is just 0. So you're only going to use the ones from the denominator because those are the values that are going to make this function undefined. It's okay if you have a 0 in the top. That's a good question, though. Yeah, so the ones that you're going to do for homework are going to have these same instructions. Tell whether this discontinuity is removable or non-removable, or it's okay if you just put whole and vertical asymptote for me. Just remember which holes are removable, vertical asymptotes are non-removable.
So why do we not include a negative 2?
Since it is in the numerator, it is okay to have a 0 in the numerator. Because what I'm looking for is what's going to make this undefined. And if I have a number divided by 0, that makes this function undefined. But if I have 0 divided by a number, that's okay. 0 divided by 5 is just 0.
So in other words, just forget the top one.
Right. The only reason we even factor the top is to see if it cancels so we can tell what type of discontinuity we have. Okay. All right. You see these right here, like example 3, a lot.
The 2 lines cancel out.
But I don't like it. Anybody want to take a guess? It's definitely going to be x equals negative 1. The question is it a whole? A vertical asymptote? Or something different?
It's a hole.
It's a whole. So isn't it always x plus 1? No.
What is that? That's a hole. That counts as a hole.
Not a hole.
Isn't that 2 holes?
Okay, so it's not a hole, also not an asymptote. What have we got here? This is a jump. Alright, so what happens here, this is what happens for these types of graphs, and they like to put these on tests. Like, I see them on a lot of relief stuff. And they put them on calculator inactive so you can't graph it like I just did. So, think about plugging in some numbers here. Like, obviously, if I plug in negative 1, that's where my issue is at, right? But let's try some numbers lower than negative 1. Like, let's say I plug in negative 5. Well, that would be absolute value of negative 5 plus 1 over negative 5 plus 1, which would be absolute value of negative 4 over negative 4, which would give me negative 1. The top would be a positive 4, but the bottom would be a negative 4, giving me a negative 1. And then if I tried negative 4, negative 4 plus 1 in absolute value bars over negative 4 plus 1. This time you're getting 3's, but it's the same thing. Absolute value of negative 3 over negative 3. That's going to be 3 over negative 3, still negative 1. Right. And so that same thing would happen for negative 3. I'd have negative 1. For negative 2, I'd have negative 1. At negative 1, this is undefined. But even if I use fractions or decimals, that same thing's still happening, right? It's something over itself. But as we approach from the left, the top is positive, the bottom is negative. But once I go past 1, negative 1, let's say if I'm using 0 here, it's the absolute value of 0 plus 1 over 0 plus 1. Now my denominator's positive, and I have 1 over 1, which is 1. And then I've got, if I plug in 1 plus 1 over 1 plus 1. I just get 2 over 2, which is also 1. And if I plug in 2, I'll get 1 and 3. I'll get 1. It's going to be the same forever. Yep, so you skip. Right there at negative 1, it skips there, causing a jump in the graph, which is non-removable. Okay. Alright, so that type of problem, just look out for it. If you see things that look like they should cancel, but one of them is in absolute value bars and the other is not, that's usually going to cause a jump in the graph. Okay, this time we're looking for f of g of x. So we got to plug g into f, right? So g is x squared plus 3. If I do g, f of g, I'm going to have 1 over x squared plus 3 plus 2. Yes. Okay, so I got to think about the denominator and what will give me 0. What will make that denominator 0? Square root of negative 5. Is that a real number? It is not.
Wait, could it be the square root?
So, like if you set this equal to 0, you would have to subtract that 5 from both sides. This won't factor, you just have to solve it. X squared would equal negative 5. You would square root both sides, but you cannot take the square root of a negative number. So, this would have no discontinuities. Yeah. And if you think about it, like there's nothing you could plug in to make that 0, because if you plug in negative 4 when you or negative anything, if you plug in negative 4, when you square it, it becomes positive. Add 5 to it, it's still positive, right? If you plug in, there's nothing that can make this 0, because any negative number, once you square it, it's going to become positive. And then you're adding more to it, so it's got to be a positive number in that denominator. So 4 does not have any discontinuities. It would be continuous for its entire domain. Okay, questions? Alright, sounded like earlier that we are a little weak on piecewise functions, so it's a good thing we are going to look at those a little bit more. Okay, piecewise function is when you take pieces of graphs and put them together. There are a lot of real-life examples where this applies. Now, they don't usually look like the ones I've just conjectured up here, but like the biggest one I can think of that we use piecewise functions for is your tax brackets or piecewise functions. So if you are in the lowest tax bracket, you are here and you pay 10% on whatever amount that you make, right? But let's say you make more money, you fall in this category, then they take a different percentage, and then a different percentage for the more money you make. So that's one where it certainly is used for that situation. Now, this particular piecewise function has no actual real life application other than just to like give you an idea of what they are, right? So if I have x over 2, how do I graph that?
Use the same thing as
It's the same as 1/2 times x, which means I just have a slope of 1/2. What's my y-intercept? 0. Right. This piece of this over here, let me highlight. These over here are just the conditions for the graph. They are not part of actually graphing it. So I'll show you what we'll do here. Well, I'm going to graph the whole graph here. It's got a slope up 1 over 2. I'm going to graph the whole thing here. But if you're doing this in pen, you shouldn't have graphed the whole thing. But I only want to use the section of this graph where x is less than -5. So I'm going to draw this in. It's not actually part of the graph, but but it helps me keep things straight. So I'm going to draw in. Why is it not? Oh, because didn't choose a line yet. I'm going to plug in. I'm going to draw myself a vertical line right here at x equals -5. I only want to use something less than -5. So I'm going to erase everything to the right-hand side of this graph right here. And I'm going to put, because this is a less than sign and not a less than or equal to, I'm going to use an open circle right there. Okay, so that is this piece of the graph right here. I'm going to use a different color for the next piece. That's just a it's not part of the graph. It's just a vertical line at x equals. Oh, it's got a y-intercept of 0 and a slope of 1/2. It gets an open circle because your x is less than -5 does not have an or equal to with it. Alright, so the next piece of the graph is the absolute value of x minus 1. So that's going to be that V-shaped graph. Which direction has it been shifted? To the right 1, because it goes opposite direction. So it's this V-shaped graph here. And so I'm drawing the whole thing, but some of you are already thinking ahead. I don't need the whole thing, right? Yeah, each side has a slope of 1. Alright, but I'm only supposed to use this between -5 and 3. So I'm going to put myself another dotted line over here at 3. Okay, and I only want the part in between those two dotted lines. So I'm going to erase this stuff over here to the left. I'm going to also erase this stuff over here to the right. For the left side, what type of circle should I use? An open circle or closed? It is closed. How do we know that? Less than or equal to, with my -5. I'm going to use an open circle over here because it's just a less than sign. I just knew it was that V-shaped graph, and since I've got -1 on the inside of the bars, it's moved that 1 unit to the right. And if it's something you're unfamiliar with, you can always just plug in numbers and plot them. So like you could plug in -2, -1, 0, 1, and plot those. So square root of x plus 1. This, for example, this one might be one you're a little less familiar with on how to graph. I'm only using this for x is greater than 3. Right? So if I wanted, what I could do here is I could just plug numbers in. So like I could plug in 3, although I do have a greater than circle. Here, if I plug in 3, I got the square root of 3 plus 1, which is the square root of 4, which is 2. So the point 3, 2, should I use an open circle or a closed circle there? Open, because I've got a greater than, it's not an or equal to. So notice that is on top of this circle right here. So, and then I could plug in 4, but if I plug in 4, weird number, let's skip it, 5. 5 is still a weird number, right? What's the next thing it's going to give me? 8. Square root of 8 plus 1 is going to give me square root of 9, which is 3. So 8, 3 would be right here. And this is just going to have this shape right here on this graph. It's that curve like this. Alright, so we haven't answered the question which asks us to tell discontinuities. So our discontinuities are at -5 and 3. What do we have at x equals -5? A jump, which is non-removable. And at x equals 3, what do we have? Whole, which is our removable. Okay. Questions? Now, what about if I had an or equal to right here for that x is greater than 3? What would that change about my graph over here? A closed circle. Would I have a discontinuity at x equals 3 if that was the case? You would not, because if you have an open circle filled in by a closed circle, then it's going to be continuous at that point. But we did not have that happen here, so. Now, piecewise functions, sometimes we don't want to have to graph them every single time. I know 8, 9. Okay, so piecewise functions. You probably do not want to have to graph these every single time, especially whenever your graph is cosine of pi x over 2, right? So another way you can deal with piecewise functions is you can plug in values. So you're going to see this on your homework a little bit. I don't like this notation, but they do it. When you see absolute value of x is less than 1, what kind of numbers have an absolute value that is less than 1? -1 up to 1. Right? Between -1 and +1, they're going to have an absolute value less than 1. So this right here, yeah. All right. So, and then what about absolute values greater than or equal to 1? Okay, so it's any number that's greater than or equal to 1 or less than or equal to 1. Right, because if you take an absolute value of a number, it could be either one. So, actually, I'm sorry, less than or equal to -1, not +1. Right, so the absolute value of -2 is 2. The absolute value of -5 is 5. Those are bigger than 1. So, I like to rewrite this, if you get this weird notation here, I like to rewrite this way because I like to put the lowest first. X is less than or equal to -1. When that happens, you just have an x. Then you got this middle part, cosine of pi x over 2. That's -1 less than x less than 1. And then the x is greater than or equal to 1. That part's also just x. A lot of times the function's given to you like this. I mostly gave you this one because our book does that for the problems that you'll be doing. Yeah, these are the same as each other here. So your possibilities for discontinuities are right here at -1 because that's one piece where the graphs come together. And then also over here at +1. So what we can do for this is we can plug -1 into both of these functions, the top and the middle. So obviously here for x, you're just going to get -1. Then you're also going to do cosine of pi times -1 over 2. So cosine of -pi over 2. -pi over 2 would be right here. Coordinates are 0, -1. Cosine is x coordinate, so it is 0. Are those equal to each other? They are not. Since they are not equal to each other, you have a jump. So you got a jump at x equals -1. We also want to test what happens at 1. So at 1, we would do cosine of pi times 1 over 2. So we're just doing cosine of pi over 2. Pi over 2 is right here on our unit circle. That's 0, 1. It is a value of 0. Does that equal 1? Because if we plug in 1 here for this x, we just get 1. No. So we also have a jump at x equals 1. If we get the same number, then it's continuous at that point. So if we get a 3 and a 3, whenever we plug it in, it's continuous at that point. So I need to adjust your homework a little bit.
You're going to include questions like that?
Yes. I need to adjust your homework just a little bit. So let's see here. It is from page 96. And you're going to do 37 through 55. Is that right? Yeah, 55 odd. And I think those last few, yeah, we're going to